Hello everyone, I am Mohammad Numan Zafar, a PhD student working with Wasif Afzal and Edward Paul in the software testing domain at Mälardalen University, Sweden. It's been an absolute pleasure to present our paper evaluating system-level test generation for industrial software, a comparison between manual, combinatorial, and model-based testing at this precious venue of the software testing domain. This paper is the result of our work that has been carried out in a research project, Adaptnest, funded by European Union Horizon 2020. Our industrial partner in this project is Alstom Transportation, which facilitated us with relevant case studies, tools, and information about the state of the practices for the testing and development of embedded systems in the railway transportation domain. The contents of my presentation include a brief introduction of Alstom, manual testing practices at Alstom, model-based testing, combinatorial testing, and tools that we have used for test generation purposes. Then I will present some related work that has been carried out to compare and evaluate these testing techniques. The research questions based on research goals, the methodology followed to achieve these goals, a description of the test case study, and result of the research questions, followed by conclusion and future work. Alstom is a world-leading manufacturer company of trains, and most of their products are software and component related to different type of modern trains. Example of trains produced by Alstom include high-speed train in China and transit train in France and Germany. All these trains developed by Alstom contain a distributed control system known as a train control management system or TCMS. It is a complex software that is built upon high-capacity infrastructure and uses standard IP technology to control and communicate with the safety and regular function of the train. The failure of such system can disrupt the normal and safety-critical function of a train and consequently can cause harm to human life. So, quick delivery with high quality products to their customer is of great concern for Alstom. Most of the development processes for the software construction at Alstom are automated and follow behavior-driven development process. The software engineer at Alstom follow Gherkin language to write the requirement specification and specify logical names for the signals used for the communication between the sensors and subsystems. To ensure the quality of TCMS, Alstom has been following TV model according to European safety standard for software verification and validation processes. It involves testing at the component level, application level, integration level, and system level. This software testing process followed by Alstom is semi-automated, where test cases and test scripts are written manually using equivalence class partitioning and boundary value analysis. In some cases, modified condition decision coverage is also used as the criteria for the creation of test cases. The test cases also follows the Gherkin format, where the test scripts uses technical signals name to force and validate the signals. The execution and generation of test results is an automated process that is carried out by using an automated testing framework and some Alstom specific libraries. Model-based testing, or MBT, is an automated testing technique that is used to generate automated test artifacts such as test cases and test scripts, as well as to automatically validate a system. There exist two types of MBT techniques. One is the offline MBT that we have used in our paper, and the other one is the online MBT technique. Both techniques use an explicit model representing a system under test to generate and execute tests. For test generation, both use a test selection criteria and a generator algorithm. The only difference between both techniques is that in offline model-based testing, the test artifacts are generated before the execution of the test on the system, whereas in the case of online MBT, the test artifacts are generated in parallel to the execution of the test on the system. For the model-based test generation, we utilized a model-based test script generation framework, Tiger, that we developed to generate test scripts. Tiger utilizes a GraphWalker to generate abstract test cases. It takes the model and an XML file containing the information about the signals, such as logical and technical signals name and their data types as inputs. After processing the information in the files, it generates abstract test cases using GraphWalker based on provided selection criteria and generator algorithm. Then it concretizes the test cases and generates a test script implemented in C# language as an output. The generated test script can be executed on the Alstom specific testing framework to produce test verdict. Combinatorial testing is a test generation technique in which tests are generated by identifying the parameters of a system and by applying combinatorial interaction strength. The combinatorial interaction strength determines the number of parameters that should be used to generate the unique combination. After the generation of test cases can be transformed or used to write test scripts that can be executed on the system under test. For combinatorial testing, we used CAGen as a test generation tool, which is available in two versions. One is the online web GUI and the other one is offline command line version. As given in this slide, it provides three state-of-the-art meta-heuristic test generation algorithm to generate the combination based on T-Bayes strategy. There also exists evidence that CAGen has comparatively high performance in test case generation due to these IPO family algorithm. This slide summarizes some state-of-the-art studies that have evaluated or compared the manual, combinatorial, and model-based testing techniques in terms of test generation efficiency and effectiveness. We have reported different studies which have compared or evaluated manual and MBT, manual and CT, and CT and MBT, but we haven't found any studies which have explored the differences and overlaps between the test cases generated by these techniques. We also find it interesting to evaluate these techniques in terms of MCDC, requirement coverage, and cost efficiency at the abstract level, testing level, where the source code is inaccessible or difficult to access. Our overall research goal for this study is to evaluate and compare these testing techniques in terms of requirement and MCDC coverage at system level in industrial settings. We also aim to examine the cost of these testing techniques in terms of test generation and execution, as well as to identify the differences and overlaps between the test suites developed using these techniques. We formulated three research questions contributing to our overall goal. The first question is related to the examination of the impact of test suites generated by these techniques on MCDC and requirement coverage. The second research question deals with the cost of test generation and execution using these techniques. The third or last research question deals with the identification of differences and overlaps between the test cases of test suites generated by these techniques. This figure represents the overall methodology that we designed and followed during our study. In step 1, we analyzed the requirement and test specification to understand the system under test. In step 2, we identified the parameters, guard conditions, constraints, and non-functional requirements such as response time. We also used our understanding to develop a model infinite state machine using GraphWalker Studio. In step 3, we developed the test suites. For manual testing, we used the test cases and test scripts developed by a tester at Alstom, which followed the similar steps earlier. Whereas in case of combinatorial and MBT, we generated the test suites containing test cases and test scripts using CAGen and Tiger. CAGen can only be used to generate the test cases in form of a decision table, so we wrote the test scripts manually. After the generation of test suites, we evaluated the test suites based on three different evaluation matrices. I will provide the detail of these matrices in next slide. This slide presents the evaluation matrices that we used or developed to answer our formulated research questions. For RQ1, we used the requirement matrix, coverage matrix from literature. We calculated the requirement coverage in percentage by identifying the number of requirement covered by each testing technique and dividing the outcome by the total number of requirements of the system under test. For MCDC, we also use the definition of MCDC from the literature and evaluated the MCDC parameters for each test suite. MCDC parameter include the condition possible outcome, decision possible outcomes, condition affecting the decision independently, and entry and exit point invoked by each test suite. We also analyzed the least dominant parameter affected by each test suite generated by these techniques. For RQ2, we examined each test suite manually and identified the common and different test cases across the test suites and developed a Venn diagram for visual representation. For RQ3, we developed a cost model according to each testing technique based on the activities defined in the literature. These activities in our cost model include the analysis of requirement, specification, modeling, test suite development, and execution of test scripts. After discussing with Alstom, we selected the requirement related to the fire detection subsystem of TCMS. This subsystem is used to detect two types of fire, internal and external, in the cabs of a train. The fire detection system uses two instances of fire detection control unit or FDCU that can have two states, master and slave. These FDCUs communicate with the sensors and receive the signals indicating the status of fire. These signals, along with the state of FDCUs, are sent to the TCMS, and based on some logical computation, TCMS indicates the detected fire on the driver test. The results of our experimentation are based on multiple graphs and tables as shown in this slide, and I will be presenting the results of each research question separately in the coming slides. Figure 4 in this slide presents the graph showing the MCDC and requirement coverage of each test suite. This figure shows that the MBT generated test suite provided higher MCDC coverage than the test suites generated from other techniques. All the test suites provided 100% requirement coverage except the one generated using two-way testing strategy of combinatorial testing. Figure 5 represents the breakdown of MCDC coverage of test suites according to the selected parameters. It shows that MBT has generated the highest number of test cases containing such test cases that can be used to test the condition affecting the decision of the outcome, whereas CT 2 ways and 3 ways provided the minimum number of test cases that can be used to detect the effect of a condition on the decision independently. Similarly, this figure also shows this parameter as the least dominant parameter affected by each test suite. We also analyze the behavior of test generation and the effect of number of test cases on MCDC. For this purpose, we generated multiple test suites using MBT and selected 3 test suites based on the minimum, maximum, and median number of test cases. Table 1 shows that MBT has a random effect on the number of generated test cases and a minimum effect on the MCDC due to random walks. While in case of CT, the number of test cases increases exponentially while achieving the higher MCDC using higher interaction strength. The result of cost efficiency is presented in table 2, in which we haven't reported the time spent on the analysis activity as there was no significant difference between these techniques. Hence, the results are based on the time spent on the development and execution activities. According to the table, CT was found to be most efficient technique in terms of test suite generation and execution, but it required extra effort to write the test scripts manually and to include expected outcome, output, and timing constraint against each test case. MBT stood second, in which modeling and redundant test cases have shown an observable effect on the time spent on the development and execution of test cases. The manual testing technique was found to be least efficient technique due to most of the manual processes. The result of differences and overlaps between the test suites can be analyzed from Figure 6, Table 3, 4, and 5. From Table 3 and 4, we observed that MBT generated test suite contained the highest number of unique test cases which are highly relevant to MCDC and will complement the manual testing to increase MCDC. Table 5 and Figure 6 show that MBT generated test suite acted as a superset of test cases and contained 71% of similar test cases on average generated by other selected techniques. We also observed that the MBT generated test cases are more similar to specification based manual testing by containing constraints and expected outcome, and it can be used to provide requirement traceability similar to manual testing. So, based on our experimental result, we conclude that regardless of test objective used to develop test cases for each test technique, each test suite achieved a substantial level of MCDC. MBT generated test suites provided higher MCDC as well as similar and unique test cases generated by other testing techniques and are more likely to uncover system level faults due to high MCDC. On the other hand, CT is the most efficient in terms of test generation and execution, whereas it requires extra manual effort to complete the test suites in terms of writing the test scripts and including the expected output. In future work, we aim to perform a thorough evaluation of the generated test suite in terms of fault detection effectiveness and also to investigate approach to reduce number of test cases generated by MBT. These are the references that I have used in this presentation. Thank you for your attention and listening the presentation. If you have any question, please feel free to ask.